You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. In this video we will learn about dynamic analysis. First of all, let's look at the dynamics page of the general data form. There are a number of different dynamic calculation methods available in OrcaFlex. We will focus mainly on the implicit time domain solution method in this video, mentioning just briefly the other 2 methods. So the default method in the program is called implicit time domain, and this, as the name suggests, is a time domain analysis. Time domain analyses are fully nonlinear and calculate the variation in system response at discrete time steps over a defined period of time. We'll talk a little more about the implicit integration scheme in a moment. It is one of 2 time domain solutions available, the other being explicit time domain. The implicit time domain scheme is usually preferable to the explicit scheme because the implicit scheme is usually much faster. Typically, the implicit scheme can use time steps orders of magnitude larger than the explicit scheme. Even though the implicit scheme is iterative, the difference in time step is usually so large as to outweigh the cost of iteration. In some cases, for instance models where very high frequency responses need to be captured, the very small time steps mean that the explicit solver may be faster, but we should stress that such cases are quite rare. Perhaps a more mainstream example where the explicit scheme is useful is for quasi-dynamic analysis. Regardless of which scheme you use, we recommend conducting time step sensitivity studies to confirm the accuracy of your results. In addition to the 2 time domain solutions, there's also a frequency domain method available, which relies on the formation of linear transfer functions, so is a linear analysis. It also doesn't move forward through time, so anything time-related, such as line feeding or releasing of line ends, is not possible using frequency domain. Back to implicit integration then. This uses an iterative method to calculate dynamic equilibrium at set intervals called time steps. The default time step is 0.1 seconds, so at every 0.1 second interval, the equilibrium position for all objects and line nodes is calculated. For every time step, the calculation is allowed a certain number of attempts, or iterations. By default, this value is 100. If it fails to find equilibrium in this number of iterations, the calculation is abandoned. The default time step is usually adequate for wave frequency responses, but high frequency events, 2 lines clashing for example, can be missed if the time step is too long. We can see that the solver is struggling if we have a high iteration count. This may indicate high frequency responses which will need a shorter time step. But how can we tell what the iteration count is in a simulation? Well, when a simulation is in progress, we just need to keep an eye on the status bar, where we see the current time step as well as the iteration count. Let's open up our previously created riser model as an example. If you haven't created this model, I would encourage you to take a look at the earlier videos in the series to help you to do this. Okay, if we reset this simulation and run it again, we can see the current time and iteration count in the status bar as the simulation progresses. This isn't always easy to see though, so thankfully there is another way, which is to access the iteration count as a result. Open the results window, select time history as the result type, then general as the object, and you'll see implicit solver iteration count as an option. Select this and press show, and a result window will be opened. If a simulation is completed, you'll see the result as a full line graph. If a simulation fails partway through, you can still view the graph, but it will obviously only be partially filled in. You can also have the window open before a simulation has been run, and then watch the graph being populated while the simulation is run. Looking at the simulation in its current state, with the default time step, we can see there are a few spikes in the iteration count time history, with one in particular above 25. So at that particular time step, there were more than 25 attempts to find equilibrium. As I said before, high iteration counts are indicative that the solver is struggling, and ideally we would like to keep the iteration count below 10 to ensure we optimize the simulation runtime. At this point, it is worth reiterating that this riser model we have built has intentionally bad behavior. It helps demonstrate high iteration counts and how to resolve them, and will also allow us in future videos to consider ways we can improve the system design. You may remember from a previous video that we can find out how long a simulation has taken to run by right-clicking on the general data form in the model browser and selecting Properties. In this case, with the default time step, the simulation time was 5.9 seconds. Let's reset this and try reducing the time step to, say, 0.05 seconds. Reviewing the properties report again, we see a simulation time now of only 4.5 seconds. And if we review the iteration count as a time history, most of the iterations are now below 10, with perhaps one exception. This simulation is probably about as well optimized as it can be in its current form, but is a good example of when a sensitivity study can be useful. In this case, comparing results of interest, such as the riser curvature or top tension, for different time steps, while also optimizing the simulation runtime. As mentioned, we will come back to the system design in another video to look at how we can improve the touchdown response. This will consequently improve the iteration count and may also allow us to return to the default 0.1 second time step. Some of you may have considered the implications of reducing the time step and rightly question why that hasn't made the simulation take longer to run. After all, with a shorter time step, the simulation has additional calculations to make. In my example, instead of calculating equilibrium every 0.1 seconds, we're now doing it every 0.05 seconds, so that's twice as many calculations. We can visualize the time steps by zooming in on a small portion of the time history using the Alt key and the left mouse button. The improvement in time is simply down to the reduction in the iteration count. Remember, this relates to the number of attempts at finding equilibrium at each time step. Note the number of iterations at each time step in this portion of the graph. You'll need to find the right balance between reducing the iteration count to a suitable level and not decreasing the time steps so much that the increase in number of calculation points outweighs the improvement in the number of iterations. I would encourage you now to pause the video and have a go yourself at varying the time step in your model and seeing the effect this has on the iteration count and consequently the simulation time. Remember, the two results you'll need to look at are the time history for the iteration count and the properties report for the general object. Finally, I would like to demonstrate the consequence of having a time step that is too long in a simulation with a high frequency event, in this case where two lines are expected to clash. In this model we have two lines suspended from both ends, one line above the other. At the start of the simulation, one end of the upper green line is released, allowing it to fall and make contact with the lower yellow line. Let's take a look at the data form for the green line named falling line. Note that end B is set to release at the start of stage 1. Note also that we have the clash check option selected. This is the same on both lines so that we can monitor for clashing throughout the simulation. When we run the replay, we see the line end being released and the upper green line falling down towards the lower yellow line. However, even though we expect one to contact the other because we have line clashing enabled, the green line falls right through the yellow line as if it wasn't there at all. The general data form shows us that a time step of 0.2 seconds has been selected. If we advance the replay one frame at a time, which is done with the Ctrl+A shortcut, we can see that as the green line falls towards the yellow line, and just before it hits it, we're at a time of 0.8 seconds. If we advance to the next time step, 1 second, you can see the green line is now below the yellow line, so consequently no contact has been observed. So just moving back one time frame, we're at 0.8 seconds and the green line is above, and then advancing forward again at 1 second, the green line is below. So, if we have a model where there are high frequency events, such as lines clashing or objects being released, we must make sure the time step is short enough to capture these. Let's try a shorter time step to see if we can model this clashing accurately. I'll use 0.02 seconds and I'll rerun the simulation. There we can see now the expected behaviour. As I mentioned before, the optimization of a model with respect to time step, iteration count, model behaviour and simulation time can be challenging, with sensitivity studies often being required to ensure results of interest are accurate and achieved efficiently. But this process does become easier with experience. Having spoken about dynamic analysis in this video, we're going to look in detail in the next video at what happens before that, the static analysis.